So here it is. The machine is done. I'm not going to show you everything today, but I really just had to sit down and crank all this out. I really couldn't just keep trying to film a video, edit a video, upload a video. I just kind of had to set the camera up. I filmed a lot along the way, and then I just basically put my head down and got to work. So what you're going to watch in the next, I'll say 3 videos, is going to be today we're going to see mostly the teardown of the machine, so about 80% of what you would need to know to just rip this machine entirely down to the last bolt. I didn't go into every detail because some things I think are self-explanatory and I'll just state what I'm doing rather than show it. The spindle teardown, so I'm going to show you, it's going to be the main topic of today's video, show you the spindle teardown, the ball bearing replacements that I went with, putting the spindle back together, and then I'll talk a little bit at the end about the next upcoming videos. So a couple spoiler alerts. I'll just kind of give you my first impressions now. This machine has been up and it's been cutting for about a week and a half now. I am running at 10,000 RPM now as max spindle speed, and I do have the 5 horsepower motor on there. I've taken some incredible cuts for me, at least for this machine. I'll throw one of those in right now. So that is about a third of the power that this machine has. That was about just under 2 kilowatts at 3.7 or 5 horsepower, 3.7 kilowatt or 5 horsepower motor. And unfortunately, the two kind of spoilers I have for you about things that didn't go according to plan was this pulley that I spent quite a bit of time making. I filmed a video about, if you watched me turning this machine into a CNC lathe and making this spindle pulley. That was just an epic failure. The making the pulley, that video that you saw, worked out great. Its actual implementation into this machine is just not going to work. It's not suited for the amount of torque that this machine has. I'll throw another video in right now. And that's what happens when a belt is allowed to slip under heavy torque and there's nothing retaining the spindle, staying in synchronous speed with the motor. So for now, this is going to work just perfectly fine for taking light cuts. It can still move about 5 times as much material as I was before, but relative to what this thing should be able to do, I have to take some pretty light cuts just to make sure that I don't over torque the spindle and start causing the belt to slip. I have on order right now, I custom ordered a timing pulley for the spindle here. There wasn't anywhere I could find that makes a 50 millimeter diameter pulley with an 8 millimeter keyway in the size that I needed. So I had to have it special made. I'm going 30 teeth on the spindle pulley, and then on the motor pulley 80 teeth or 80. So I'm going to be 2 2/3 to 1 ratio, 2.66 to 1 ratio from motor to spindle once I get that on there. And it will be synchronous. It's going to add some noise, which is not ideal, so I'll probably end up enclosing this upper portion here to keep some of the noise away from me. But it will ensure that I always keep synchronous speed with the motor. That's going to allow me to do things like tapping on the machine, low speed facing with really good depths of cut, and not worry about that slipping. So that didn't work according to plan, and in a future video I'll show you the upgrades to the new motor, or to the new spindle. The second and really the last thing that just didn't go according to plan was the spindle pulley the spindle bearings itself. So you are going to see a bit of that video today. I originally decided I was going to go with deep groove ball bearings in the top 3, which is stock from Precision Matthews. I just went with some nicer, higher speed rated bearings, and then in the bottom I was going to stick with tapered roller bearings, and in the video a couple times I call them angular contact bearings. So tapered roller bearings are a form of angular contact bearings, but to be more specific I should call those tapered roller bearings. So that is what Precision Matthews ships stock with the machine, is 2 tapered roller bearings in the bottom half of the spindle assembly. You'll see what I'm talking about in a bit. And that accounts for any axial thrust or axial load from drilling and tools trying to pull the spindle down and things like that. Stock from Precision Matthews, those pulleys are like packed with a thick axle bearing grease basically, and that I was afraid was the thing that was limiting the speed of the machine. And I thought that maybe, I even stated in one of the clips here that I might delete or edit out, but I stated at some point that I thought maybe if you just repacked those with like a Kluber Isoflex, a high quality, high speed spindle bearing grease, that maybe you could achieve a higher rated speed, like 8,000, maybe 9,000 RPM. That's wrong. There's no way you can use the stock tapered roller bearings to get anywhere over, I'll say conservatively, 4,500 RPM. So if you manage to squeeze another 50% out of your stock motor, then go ahead and try to stick with those stock tapered roller bearings with some new grease, and maybe that'll do for you. But what I decided to do was replace those bearings with some SKF bearings, some nice higher quality tapered roller bearings, and I did grease them with the Kluber Isoflex, the right amount of grease. I gave them the right amount of preload, and then I tried doing the spindle warm up, which takes about, or the spindle run in, which takes about 3 hours at varying RPMs. Anything over about 6,000 RPM, the spindle got so hot that it actually stalled the spindle itself, or seized the spindle from the growth of the bearings, and caused the belt to start slipping over this pulley, like I said, and just was not a good thing. So long story short, those bearings are gone. I now went with a true angular contact ball bearing. Each of these each of these ball bearings was about the cost of all the other ball bearings put together. So these are two high quality NSK super precision ball bearings, angular contact bearings. But up at 10,000 RPM now, I barely get to the point where I would consider this really warm. Definitely not hot by touch. The highest temperature I've read, and I've gone 10,000 RPM for about 45 minutes continuously, is about 160 degrees, which is certainly not room temperature, but the Kluber Isoflex, that grease I'm using, is good to like 250 degrees, so I'm nowhere near rated temperature. The added benefit, because there's so much less friction from the balls compared to those tapered or those angular contact rollers, is that there is so much less friction in this spindle. I can actually, if you have a Precision Matthews, you'll know what I'm talking about. You could barely get like a 1/16 of a turn free spinning on the spindle, because it was just so tightly bound in there from all the friction. I can get like 1 or 2 full turns just by giving it a good flick now. So just that alone can show the difference in the amount of friction that's built up in the spindle. And obviously friction becomes heat. Heat becomes changing in dimensions and tolerances, and is really bad for a CNC spindle. So if you're following along, ignore anything I've ever said about using the stock bearings, about going tapered roller bearings. Go with, I'll put the part number in the video description, go with some precision angular contact ball bearings, and you will be happy. I would say that you'd probably be good with these bearings up to 12,000 RPM. I'll try it up to 11,000 RPM when I get the new spindle pulley, because it's a little bit higher of a ratio. I don't think I'm going to leave it at 11,000, because 10,000 RPM is really more than I ever would have asked for in this machine. But just for completeness, eventually I'll try 11, maybe even 12,000 RPM, just so I can give you guys a recommendation on what the bearings could take. So thanks for coming along. We'll get through this video. It takes me forever to do these simple edits of these videos because I'm so bad at this software. So a lot of this footage is filmed. The entirety of where I'm at now, I have documented on camera. I just need to get to the point where I can get it all compiled together, make the simple edits that I do. I don't have explosions and sound effects going on in these. My video quality isn't great, but I really just am bad at the video editing side of things. So it takes me a significant amount of time just to get you guys a video out, and I apologize for that. So hopefully you guys will be able to see through fruition every step of the way to get the machine to where it is now. I have about 250 inch per minute rapids on the machine now with the servos. I have 10,000 RPM with the spindle, and this thing just flies compared to what I'm used to. So today we'll do spindle bearings. The next video is probably going to be epoxy granite. I've got a lot of requests about the epoxy granite fill. And then the video after that, probably servos, reassembly. And then after that, I would love to film some cutting stuff for you guys. So please, in the comments below, tell me what you want to see this thing cut. Tell me some speeds and feeds. If anyone out there has a Tormach, an 1100 or an 1100 MX, I would love to put this thing head to head with a Tormach. So send me your videos, send me your ideas, and I will, I mean, within reason, I'll cut anything you guys want me to on this machine, just if you're interested in the limits, because I certainly am too. So thanks for sticking by again, and I'll see you guys in the next one. Okay, well I feel bad about not capturing all the spindle disassembly, and to be honest, it was something I was really interested in when I started this project, is how easily this comes apart, and is it going to be a huge pain in the butt to take the spindle out and replace the bearing. So I feel like I'd be remiss to, I guess, steal that away from you guys. So I've decided to take the spindle mostly back out again, at least to the point where I can show you guys the internal of the spindle, show you where the bearings are located. I'm not going to take the upper portion of the spindle out because you can see that pretty easily through here, so I'll get some up close shots and sort of explain what's in there, and that is a press in and out, which I really just don't want to do again, and I don't think there's much benefit from it. So I'll take the lower housing of the spindle out. I actually, like an idiot, forgot to grease the angular contact bearing, so as much as I'll pretend like I'm doing this exclusively for your benefit, I do have to grease those anyway, which requires me to take the lower housing of the spindle out. So we're going to go ahead and do that right now. I also took out the quill downfeed assembly parts. I'll show you on the other side the other piece that came out, but the housing, or the head, is entirely empty now, with the exception of the spindle. So I think that's how I'm going to leave it in the end. I'm going to take this out and just put a bolt in there that I can cinch down real tight. I have no need to ever extend the quill on this machine, especially after the CNC conversion was done. So there's really no need to keep all those extra components in there, and it just kind of gets in the way. I'm going to make a new faceplate here, and that little protruding nub that I'm never going to use was just stupid to have in the way for no gain. So let's see how this works out. So what we're going to do here, it's pretty straightforward. The nut up here is, pardon the really stupid big gloves, they were free, and decided to waste a pair on this. So this is the nut that's holding the whole spindle assembly in. So it's externally threaded on the quill shaft of the spindle, and then this little housing nut is what needs to come off in order to drop the spindle out. So you do need to stabilize the spindle itself somehow. There are flats on the side here, what you would normally use to change the tool. This is the tool provided by Precision Matthews. It's a big piece of crap, but it does stabilize the spindle enough. There's a ton of clearance. You can get like 1/8 of a turn until you actually contact the flats. So it's a big piece of crap, but it does work. So just going to stabilize the spindle with this wrench, and then with anything else, an adjustable wrench or something, you're going to thread off this nut right here. Now this is a pretty major warning when you're doing this. I'm going to move the camera, sorry for some motion sickness. You want to place something below the spindle itself. Once you unthread that nut, there's actually nothing other than the friction from this locking clamp that's holding the spindle from free falling down onto your table and really doing some damage that you don't want to deal with. So I have this tightly clamped right now. There's the dog freaking out. I have this tightly clamped right now, so it should retain the spindle while I'm loosening it, but just in case, I have a foam pad, a high density foam pad under here that should absorb any impact if it does fall, and it gives me something to rest it down on. The other way to do this, which I'll probably end up actually doing, is just lower the head down as close to the table as possible so there's no room for it to fall. So let's get to it. You can also take the drawbar out right now, and any collets or anything else that's in there. Forgot to do that, so give me a second. Drawbar and TS collet out. This is off, and I did misspeak. I forgot, I'll show you in a second. There is a spring clip up here that retains the spring to prevent it from free falling, so there is one more step you have to take to get the spindle out. Okay, so up here you're going to need something to push this collar down, but basically you're just going to push down on that spring, and then if you can see the E-clip here, push that down and out of the way, slowly let off. And there we go. So this E-clip is holding that captured, this E-clip right here is holding that captured spring assembly in, which you can remove. This is the quill return spring, and you can see this is heavily packed with some like axle bearing grease that was coating the entire spindle. We'll talk more about that when we get the spindle out. Okay, and now it should be as easy as slowly loosening this, supporting the spindle so it doesn't free fall. Now that it's loose, you can see that's just dropping right out of the spindle housing, and I'm going to raise the head out of the way. Again, support the spindle, and it is free. Fairly heavy, so you just want to be careful with it, but this is the entire lower assembly of the spindle cartridge. So you have your quill right up here, and then the actual R8 taper down here. I did, kind of late developing news, I did locate a BT30, it's actually NST330 taper replacement for this, and I may end up swapping to that at some point if I think BT30 is going to be essential for this build. Sorry, this is out of frame. In order to make it work with BT30, I would have to modify the pull stud arrangement on that NST30 taper quill that I have spec'd out, or that I found, but we'll see if that ends up being needed or useful. But for now, we're going to tear this apart. So it's as simple as unthreading this bearing retainer nut right here, doing the same for this captured bearing retainer nut up here, and then the only thing holding the spindle inside the spindle housing is the actual press of the upper and lower angular contact bearings. So we are going to have to press this shaft out in one direction in order to get get access to both bearings. I apologize if this totally nauseates somebody. I'm going to go handheld for this. So while we're at this part of the build with the spindle quill removed, the lower assembly of the spindle, try to shine a light up in here, see if you can see any of this. So that is the inside of your spindle with the quilled mating surface on the upper spindle. You can see that new bearing that I installed up there for the upper assembly. And then I'm trying to shine a light in here so you can get some sort of vision, and trying to do this all through the viewfinder. But you can see in here, camera, or the light might get in the way. Maybe you can't see. I might have to find a better light. Give me a minute. Alright, I think this is a little bit better. I changed the brightness on the camera. See if with a flashlight. Okay, that should be plenty good. So you can see in here, right down there, that green thing you're looking at is the lower bearing. So that's actually a double stack of those deep groove ball bearings. So the one that you saw from underneath is not that one. They're stacked on top of each other, so there's two bearings right there. And then right up here you can see another set. Sorry, I just misspoke actually, thinking about this. That is the bearing that you saw from below. Up here is a double stack of deep groove ball bearings. So right there you have two bearings supporting the, so this is the spinning part of the spindle. So this is what your motor is attached to. Sorry for the autofocus. This is what your motor is attached to through that quill below. It spins this part of the housing, and then that allows that to transfer the motion of the motor to the quill that can actually move up and down. So that spline shaft extends through here, and then it allows it to lower and raise while it's spinning. That's the reason that there's two assemblies in here. Those three divots that you can see in the upper assembly right there are for the encoder race from the stock brushless DC motor. So there is a RPM readout on this, and that's where it mounts to so that it can have that light sensor and verify the spindle speed. So in order to remove this, it's a little bit tricky. You would have to remove this, whatever you have mounted to your spindle, excuse me, most likely the stock pulley. So this comes off, the keyway, or the key that's in the upper assembly comes out, and then there is an E-clip down here. I don't actually think you can see right there, that's where my belt burnt up. I am going to go to a timing pulley, so that'll end up going away. Wasted time making this, but whatever. You can't really see it right down in that groove right there. There is a face E-clip or spring clip, so you have to pinch that together and then remove it, and that's the only thing retaining that upper assembly from coming out the top. Now these bearings are pressed in both upper and lower, so the way that I did it is I took something, hard rubber. This is a screwdriver, it's not what I used, but took something hard rubber, stuck it up in there so it was against the spline part on the inside of the shaft. Really wish this focus would do a better job. And then once it was... Can I adjust the focus on this? Sorry, new camera. Trying to mess with this while we go. No. And then while that was up in here against that, I lowered the head and it just pressed those bearings. Man, this focus is terrible. I really apologize. And it was able to press these bearing stacks out. Now I didn't want to push this bearing through both the press fit down here and the press fit up here. So once it broke free, I actually removed that bearing from the assembly. So I stuck braces up here so I could press the bearing out as it removed, and then the bearing slid out and I took this upper assembly out together. You could also just press the whole unit out as one if you wanted to, but that's really up to you. So once that part is out, it's just a matter of pressing those two bearings in the top out, pressing this bearing off the bottom if you hadn't already, and then pressing new bearings in, and that's the whole upper assembly done. So we're going to walk over to the lower assembly now. I'm going to work on this autofocus, and I'll see you in a minute. So here we are doing the spindle for the third time. So right now I have the spacers. So these spacers, these are for the smaller end of the bearing. Those are installed down here in the against the shoulder of the lower bearing right here. So let's pause here for a second. Now that I'm watching this video, I guess I never really explained why I have spacers at all. So the new angular contact bearings that I got are actually 4 millimeters each thinner than the stock bearings from Precision Matthews. So in order to get the correct spacing, I had to install 4 millimeter spacers on the upper and lower bearings to make them the correct width. After I did this, I actually found out that the lower bearings, the one I'm about to install closest to the R8 taper, actually didn't need the spacers at all. That 4 millimeter less in thickness was actually perfectly fine, and I kind of wish that I hadn't installed those lower spacers. It makes the bottom jam nut that locks the lower bearing in place protrude from the face of the spindle again. So if I were to do this over, I would not install spacers on the bottom bearing, but I would 100% install 4 millimeters worth of spacers in the upper bearing assembly. And now I have to press the bearing on to the lower part of the spindle. I am heating that just in a crappy toaster oven, which should work fine. So I'm going to heat that on, press that on, turn this upside down, and press the whole bearing stack into the spindle, and then we'll tackle the top end of the bearing. So it got it removed much like before. I've got my Isoflex there. I'm going to lube these probably before I do this, and we'll see what happens. Okay, with the lower bearing fitted on. This actually went on basically by hand with no heat. Just need to make sure to get it straight aligned, and it slipped right down. If anyone needs to know the part number for those steel spacers, that's what I've got. And now we're going to fit this into the spindle housing. Okay, so to do the upper bearing, we've got the spacers. Slide those on. Of course, I got them so misaligned that they won't slip down because I'm trying to film this. Okay, so those are sitting at the bottom. And then, angular contact bearing, you can see the nomenclature is on the bottom. The outer lip here, where it says England, is thicker on the bottom than it is in the top. You can see that. So that's going to go down, so text down. Get that mostly lined up like that. There we go. I felt it push in. And now that it is seated, oh, there we go. Seated on the outer race all the way, we are going to preload it using this nut. So you can see the raise section right there presses on the inner portion of the bearing. So that goes down, and this is threading onto the actual quill shaft, so the moving part of the spindle. And then I'm going to tighten this down to set some preload, about 100 inch-pounds or so, so nothing excessive. You're not trying to crank this down through the bottom of the spindle. Okay, the way I like to do this is I like to use the machine under power to help me remove the head. So I'm going to start by loosening these bolts that hold the head onto the machine. That's going to allow this head to tilt. I'm going to put it on its side, on the flat side here, so that it's perpendicular to the current orientation. I'm going to set it down lightly on this wood block, and then I'm going to use the table to actually help me pull the head off the machine, so I'm not awkwardly trying to suspend all of this weight out in front of me. So here we go. So this is tapered, so the smaller part is what goes down, and as you drive this in further, you're going to tighten the gib there. So you're going to want to remember the orientation of this. The top is the thicker side, and the bottom is the thinner side, and then obviously this little notch right here has to align with the cap bolt, the cap head bolt right here, so that's how you make sure you know the orientation of this. These bottom two bolts are what hold the current air strut onto the head of the machine. That's going to go away, so these will never be used again. And then the top two are what hold the saddle for the Z-axis onto the actual double nut. So this is the entire driving force of the Z-head is into these two bolts right here. So as you loosen those, be careful that this doesn't just free fall. Wouldn't be the end of the world, it'll absorb plenty of it at the bottom there in the bellows, but you don't want it to ding anything. So it is actually a bit captured in there just based on the design of that nut, so I'm not too worried about it. But with those removed, you're then just going to pull up and away, and there you go. Something to note when you're trying to take the table apart, so this is on the stock mill or after conversion. When I put this back together, I'll kind of show you how to convert your machine to CNC if you were going to put a stepper motor kit on it like this. But something important to know is what you don't want to try to do is unscrew your lead screw from one of the ends. So either remove the mount that mounts the stepper motor, or what would be the hand wheel on this side, or the same on this side, and then with that mount removed, try using the lead screw and either manually cranking or with the stepper motor to slide your table off the machine using the screw. What that's going to mean is your ball screw is just going to, or your ball nut is just going to run off the ball screw, and you're going to lose like 130 balls that you need to repack into your ball nut. So absolutely don't do that. The way to get your table off is as simple as removing on both sides. So cracking on this kit these 8 socket head cap screws, 4 on each mount, and then with these removed on both sides, I'll show you in a minute, you just slide the table off the dovetails. You're going to want to loosen the gibs a lot and take the gib itself out. This way there's a lot of slop in the table, and then from there you just slide the whole table off and it'll come out and leave the whole ball screw behind. So, what if what I said before happens to you? You have these ball nuts, you accidentally take something apart wrong, and you get a ton of ball bearings sitting in a pile. You can't actually see them down here, can you? I'll flip it this way. And you find out that you have a whole bunch of ball bearings that you end up playing 52 card pickup with all over the place. And what do you do now? You have an empty ball nut and a whole bunch of ball bearings everywhere. How do you refill them? So if you don't know how these are designed, these little orange cups here are the recirculating grooves. So there are different tiers of balls in here. They all recirculate in there and just move around in a circle. So if you were to try to just pick these up, get a nice pair of flat nose tweezers. If you were to just try to pick these up and place them in here, you're going to have a fine time filling them up around the bottom of the lip until you get about halfway up, and then every time you put a new ball on, it just falls back into the center of the ball nut, and that's entirely a waste of your time. You're never going to be able to get 360 degrees of this filled doing it that way. So there's a couple different options to do it. So in this container here, I just have a big dab of petroleum jelly. You can use KY or this crap off-the-shelf brand stuff. But a dab of petroleum jelly works well. You can use axle grease. You can use all sorts of different things. You want something very thick and viscous so that it captures the balls. So what I'm going to do is take this half of the ball nut. I'm just doing this sort of to show you guys. There's no reason for me to do this. And oh no, you slipped your ball nut out the end of your ball screw, and random number of balls are falling out of there. And then if you turn it over to look, a whole bunch more fall out. So I'm just going to get all these to fall out of the bearing into that cup. Now this is convenient. I'm not doing this like real life where these go all over the floor and you have no idea where they went. So I'm dumping all these into a Tupperware. It happens to be the one with that Vaseline already in it. Okay. I've actually done this before in the past, and that's why these are kind of having a hard time coming out of here. They are a little bit thick in there. Okay, so that's 2 empty bearing races. One of them sitting in here, and the rest of the balls sitting down there. So I'm going to go through and just clean out this bearing here. You want to use something that's lint-free. This is a lint-free rag. Try not to use paper towels or anything like that because you really don't want anything in here. It's not the end of the world if there was some debris in here. These are really robust and hardened balls and hardened raceways, but try to be as clean as possible. So get that cleaned out, and then you take your object that you're going to use to repack it here. You can again just use the ball screw. That's just a bit tedious and hard to manage, so instead I am going to use the this rod that I have here. So you're going to slide this in. You're going to start toward the end that has this white colored or plastic piece here. That's the wiper to make sure debris doesn't get inside the ball nut. So you're going to start down there, which is the end of the bearing, and then maybe I'll try to get a better view for you guys. Okay, you can actually do this first ring without that in there, and I'm going to do that coming from this side so that the race is closest to me. So you're going to take the closest, sorry I'm out of frame, you're going to take the closest recirculation ring right there, and that's where I start packing the balls. It makes sure that they're all in the actual raceway and not inside the grooves that the threads are going to ride in. So just take one at a time. Here, I'll get a little closer to you guys. Take one at a time. I actually picked up 2, that's okay. And you're just going to pack those down in there. Okay, we have to take a quick pause again. I lost some more footage, so battery died on the camera again, wasn't really paying attention. It wasn't worth reshooting. Basically I just repeat this process and put the balls in until that whole set of ball bearings is filled. I think it takes 21 per ring, and there's 3 rings in there, so there's 63 balls per double nut, and then there's 2 of those per ball screw. So you have to put in quite a bit, 126 balls per double nut ball screw, but it goes pretty quick once you get started. Just continue on filling them in that recirculation groove until that whole cavity is filled, and they stay in there pretty well once you have that Vaseline in there. And just like the one for the Z, this is tapered, so the taper goes in from right to left in this machine. From here, you basically you have an option to go one way or the other, but you basically want to lift the table up just a little bit to make sure you clear the ball screw, and it is cantilevered sitting on top of the the machine right now, and then you can either slide it one way or the other. In my case, I am going to slide it this way because it's easier, because I already have this side of the enclosure removed. And then just be careful as it gets toward the end. You are going to end up taking, obviously, the whole weight right about there. Now to remove the ball screw, this is just held in place with 2 socket cap screws on the end here. Sorry to get in the way of the camera a little bit. I'm going to take these out. 2. And then this ball screw is just going to lift straight out. Like that. And here on our y-axis, we're going to remove the gib. We've already loosened that. Again, tapered, goes in from front to back, so the thinner side is in the back there. Once those 2 gib screws are removed, as well as the gib is pulled out, there's just 2, you can see that wobbling because it's not connected or not tightened with the gib yet. There are 2 bolts down in here. And the Z column. So this is held in with 4 bolts in the back. You need a 12mm Allen to remove those. So I happen to have a set of ratcheting large metric sized Allens. Now this, I already removed those 4 bolts, so this is basically just held in under its own free weight right now. As you can see, that's not super sturdy. The only annoying thing about this is the gas strut that's come stock from the factory that I'm no longer going to use. That is bolted into the base and then it extends up to the column. So I can't just tilt this forward and then slide it out. You actually have to lift it up and over that Z or that gas strut, and then it's free. It's self-sustaining from there. You can remove it from the machine. But I'm going to try to kind of tilt it a little bit and see if I can slide it up and over. This may be a little precarious, so if there's a crash, you'll get to see it. Okay, last step. I unbolted the 4 bolts on the base casting here, and now I'm just going to remove this from the enclosure, and then it's done. The enclosure is, as you can see here, just kind of free sitting on top of the base.